So thank you for the introduction and thanks for offering me this opportunity to talk. I will just pick up from where Joey just ended. Let's recall what you saw 3 minutes ago. So together with Joey and Sue, we proved that a Tor complex event space can be extended to a Tor manifold if and only if this holds. Okay, so as a grad student, what am I going to do next? Generalize this to a general complex event space. So if I'm only allowed one sentence, I will say after the correct modification with the definition and a similar technique with slight change, everything will work out. But since I have a general of 8 minutes, I'll explain to you how I will make those assumptions. Okay, so first, what are other complex event space? As Joe explained, an orbit of complex event space is short if there's no other orbit in the same moment fiber, otherwise it's tall. And Sue and Ia observed that the moment image of the short orbit could only be on the boundary of the moment polyton. So we define a complex event space to be maximally short if it is short wherever it could be. And I will use M divided by T short to denote the set of short orbits. Okay, so this part is just definition. What do I need to change in the conditions? So it turns out there's only one thing I need to be changed about the K colorability or 2 colorability. But to do that, we need to define what exceptional orbit is and what skeleton is. So Joey didn't have time to write it down, so I write it down for him. So we say an orbit is exceptional if the stabilizer is larger than you expected. And we use the collection, we use X to denote the set of exceptional orbit, and this is called skeleton. 2 quick examples. If you consider the standard T2 action on CP1 cross CP1, I can choose some different subcircle. If I choose a second copy of subcircle, I'm projecting that to the vertical direction. This gives me a tall complex event space with no exceptional orbit. So here I'm actually following Yale's convention by projecting vertically, not horizontally. And I can also do this by choosing a different subcircle. I can choose a subcircle of diagonal subcircle. And this will be maximally short, and there will be 4 exceptional orbits corresponding to 4 vertices, or 4 fixed points. So, and as Joey do, I kind of group them into 2 groups, but actually here secretly I'm doing that in 3 groups. As you can see, there is a red vertex, a blue vertex, and 2 black vertex. So this is exactly the change I need to make. So I can only color things in some sense in the interior, but not on the boundary, because that will mess things up. So let me give you the formal definition. So I will say the skeleton is K colorable if I can divide the set of components of the skeleton, of the tall part of the skeleton into K parts, so that on each part the moment image is injected. So you may ask, okay, why do I need to remove that? But before I even talk about it, let's verify I actually gave the same definition as Joey do. If the space is tall, no short skeleton, so this is exactly the definition Joey gave you. Okay, great. I'm not doing something wrong. But then why? So there are 2 reasons. First reason, let's say the definition of exceptional. We say an orbit is exceptional if every nearby orbit. But what if there's no nearby orbit? Then that's tautologically true. So short orbits are exceptional are kind of for like different reason. They are tautologically exceptional. They are not exceptional because of the comparison. Another reason why I would need to remove that is I want the intuition to be correct. As Joey told us, when we do the projection, we have like ceiling part and the floor part. So we do want every complex event space that comes from a Tor manifold to be able to be 2-colored. But that will only be feasible if I remove the boundary. If I do not remove the boundary, things will go wrong. Why? Let's see some example. So I'll focus on the bottom example. So this is actually CP3. I project that to some complex event space. But I choose a very specific torus. So in this specific torus, I have 3 exceptional sheets on top and 1 exceptional sheet on bottom. And when I do this projection, I choose it very carefully. So on the boundary, every orbit is short. If I do not remove the boundary, then the boundary glues the ceiling and the top. So the skeleton is actually connected. But the moment agent will not be injective on the skeleton. So that will mess up our intuition about 2-colorability. So that's why I have to remove that. Okay, after this adjustment, I can state the result. I will call a complex event space subtoric if it comes from a toric manifold by restricting to a codimensional 1 torus. So, and my theorem says, the skeleton of a complex event space is 2-colorable if and only if there exists a subtoric manifold with isomorphic skeleton and same to its maximum measure. I want to put a remark here. This is not an criterion for extension. So one of the reasons why we have the criterion there is because the classification of tau complex space is already out. But for the general case, it hasn't been published yet. But we do expect similar result to hold. Another thing I want to say, kind of independent of like this thing, is kind of a cute observation. I think that's cute. Probably you don't think that. But the thing here is, if I insist on the complex space to be maximally short, and if there's extension, then this extension is unique in some sense. So up to weakly equivalent isomorphism, I do have some sketch of proof, but that's not the focus I want to be talking about. I will be using the rest 2 minutes to tell you how I will adjust the proof compared to how 3 of us will be doing it. So basically what I will be doing here is, we got the same general idea. Start with complex event space, get a label graph. We use this graph to build a Delta polytope. But I will build the graph in a different way compared to 3 of us. So I actually list everything in the table, but I feel sometimes it's hard to read the table whenever there's too many words. So in short, what do we do? 3 of us, we got a 2-colorable complex event space tau. Separate them into 2 parts. Of each part, we get a graph. And from each graph, we build half the delta polytope. We have 2 half delta polytope. We piece them together, we get the delta polytope. So this largely relies on the fact that the space is tau. This is because the ceiling and the floor does not see each other. So if you have something that's in common, you cannot easily separate what ceiling is and the floor is. So that's why I can only do 1 graph. I need to put a lot of extra information here to keep track of which vertex is on the ceiling, which vertex is on the floor, which edge is on the ceiling, which edge is on the floor. I also have vertices both on ceiling and on floor, and edges both on ceiling and on floor. So if I give you this example, what 3 of us will be doing here is separate them into graphs, build 2 half-delta polytope, glue them together. And what I will be doing here is I get a very complete graph, but this graph is abstractly the graph of the delta polytope I'll be building. Then I just need to lift all the labels to make sure that works. Thank you.
So it's my pleasure to welcome Shabtai, and he's speaking to us about off-diagonal estimates of partial Bergman kernels on S1 symmetric data networks.
All right, so thank you very much for the opportunity to speak here. I'm really very glad to be here. It's my first time in Toronto. And right, so I will speak about what appears in the title. So let me begin, please. So by now, we've actually seen these kind of settings already, thankfully. So, well, for me, these are the standard setting to consider geometric quantization, namely on Kähler manifold, but of course, this is only specific settings. So we have a closed connected Kähler manifold, n-dimensional, complex dimension, and we have a pre-quantum line bundle. So so as we've seen, I think earlier today, and then all right, and then the space of I have this pointer and it even works. So then the space of holomorphic sections is so what's perhaps not been considered. Oh, I'm clicking the wrong thing. So what's not been considered earlier perhaps are these high tensor powers of this line bundle, which for me is sort of the main point of the story, because I want to study partial Bergman kernels as this K, this tensor power, goes to infinity. So as written below here, so this K goes to infinity, this semi-classical limit where we can sort of expect these Hilbert spaces along with self-adjoint operators to somehow approximate sort of the classical system that we began with. And I will be considering a Schwarz kernel of a very specific operator. So what is a Schwarz kernel? It's essentially an integral kernel. So the action of the operator is given by integrating with respect to the Schwarz kernel. So for a general endomorphism, so we can express a Schwarz kernel as follows. And here there is a slight abuse of notation, namely I denote the Schwarz kernel of an operator and the operator in the same way. And the partial Bergman kernel is just a Schwarz kernel of projection onto subspace of holomorphic sections, and this is a very general definition of a partial Bergman kernel, and so probably it's not very useful in this full generality. I mean, I don't think we can say much in this level of generality, but so I will restrict to specific case of partial Bergman kernel. But before that, I couldn't not mention that. The term partial Bergman kernel, it references the full Bergman kernel, which is a Schwarz kernel of identity, or alternatively, Schwarz kernel of projection from L2 section to holomorphic section. And sort of Bergman kernel is an important object in complex geometry and in this theory of quantization specifically, but so many things, or sort of important. Oh, again, I clicked on something. So sort of important object, and what I think it's worthwhile noting is this diagonal behavior, right? So this Schwarz kernel are sections of a line bundle over the product manifold. So in particular, we consider as values on the diagonal, and then okay, we identify with the seal over the diagonal, but then we have this leading order term is this k to the power of n over 2 pi, and then so this is leading order behavior. So until what time do I have? So just I don't, because there is a very important picture. So this is the whole point of the talk, and I don't want to miss it. 06. So there's like 4 minutes. Okay, hopefully it will work out. So right. So I will consider the following settings. So we have effective, doesn't necessarily have to be effective, but for 8-minute talk it has to be effective. Holomorphic Hamiltonian circle action, and then we have this normalization where the minimum of the Hamiltonian is 0, and we define this quantum observables, right, originating in this smooth functions, the momentum map. So and then we quantize, we get this self-adjoint operator, and we have this equality where we don't need actually to apply the projection. Already this operator preserves holomorphic sections, which is very nice. And then we know the spectrum, and we have unitary representation and so on. So it's nice settings. And then the partial Bergman kernels that I consider will be Schwarz kernel of projection onto subspace spanned by eigenvectors of this operator, which correspond to eigenvalues greater or equal E, right? And then the motivation is that this kind of operator, first of all, I mean, it can be related to a domain in phase space, so specifically this domain, and so sorry for clicking. And then also it turns out there is some motivation from quantum Hall effect. So now I can state, first of all, previous result by Zeldich and Zhao, where they consider the behavior of this Schwarz kernel over the diagonal. So there are some notations here that we need to sort of absorb. So first of all, there is this gradient flow, because we want to also look in gradient. So we will look near. So we will look in points. Oh, it's written here, right? So point over the level set of h equals E, and then we want to perturb a little bit in gradient direction and see what would be the behavior of this partial Bergman kernel. And Zeldich and Zhao, they found that over the diagonal, the behavior, we have this complementary error function profile. So this means essentially that we interpolate between this partial Bergman kernel over the diagonal, interpolate between being completely negligible, so almost 0, and then recovering the full Bergman kernel, so essentially almost identity when we go in gradient direction from this critical value E. And then my result here is off diagonal, so sort of completes the picture. Again, we look at the point right on this critical value. So not critical, so I mean specifically on this value over the value E. And now we allow to go in 2 gradient directions because we are off diagonal, so we don't have. So we have 2 parameters A and B. And again, we go in this gradient direction. And so earlier we had this complementary error function factor, and now we have this sort of Gaussian factors. We have this kind of Gaussian bump that we will see in the picture, and then we have this cotangent term here. So maybe I should already go to the to the picture so we don't miss it, right? In this 30 seconds that are left. So yes, I mean basically the theorem. So somehow we can look at the picture. So the theorem says what we see in the picture. So the picture is just an example for the specific case of rotation of the two-dimensional sphere, right? So this is sort of a standard example to look at. So these are just the settings of the sphere, and this also says that the sort of the approximation is sort of good, so the error goes to 0 as in the way that we would expect it to, according to the theorem. And sort of this is a picture that I was hoping to be able to have enough time to show, so here I fix 1 point. Yeah, okay, it's okay. Sort of. Yeah, I'm actually done. So this is sort of the picture that I wanted to show. So the first result was on the diagonal where things are significantly larger, but along the Miltonian orbit we have this also this non-negligible part. This is for a single eigenspace. Some references, and thank you very much. Oh, and also happy birthday, of course, to Yael.